So last time we were finishing up, we started talking about at the very end many electrons or multi-electrons. Many electron atoms, and we talked about why, oops, except you can't see it. We've talked about a couple times why it's difficult to deal with many electron atoms and why we can't solve these systems exactly. So cannot be solved currently. And we came up for some reasons why, and they couldn't be solved exactly. So what were the reasons? Does anybody remember?
Electron correlation and electron exchange.
So electronic correlation. So can anybody tell me what electronic correlation is?
Is that like the direct interaction of charge?
I wouldn't say the direct interaction of charge. Well, can you be a little more explicit on that?
The position of each electron relies on the position of the other ones.
Yes, exactly. That's it. And then we have electronic exchange. Oh, exchange. There we go. Which we talked about in organic a little bit, but we haven't gotten to here. And what we said is it's a consequence of the Pauli principle. And do you remember what the Pauli exclusion principle stated? Could anyone summarize it for me?
They cannot, an electron cannot be in the same exact state as another one.
Right, so they have to have different sets of quantum numbers. Can't be in the same quantum state. So this comes about due to just quantum mechanical properties. And we're going to show the mathematics behind that. In inorganic, I was pretty hand wavy and didn't explain it too well. The reason is it's really just a mathematical consequence. It has to go with something called asymmetry, which we're going to get to in a bit. Before we do that, we have to talk a little bit more about like the Hamiltonian of a multi-electron system. We have to review determinants and how to use matrices again. So we'll do some fun stuff. Okay, so in order to solve these things, to solve these systems, so if we want to solve this stuff, what do we got to be able to do? Or what are we going to have to do?
Make approximations.
Yeah, we got to make some approximations. So when what you're doing doesn't work out, you have to approximate some stuff to make your life easier so you can solve. So we must make approximations. The first one we're going to talk about is the orbital approximation. And there are some physical chemists that get really upset about how orbitals are described. If you took general chemistry from me, I always describe them as a mathematical function to describe the wave-like behavior of an electron in an atom or a molecule. The reason for that is sometimes people will say, like, to give this idea that it's like a balloon and you're just dumping electrons into it. What it really is it's a mathematical function. It's due to an approximation that we have these orbitals. So it's a theoretical construct. So let's start off with what we all know. The wave function of a multi-electron system is very complicated. Wave function of a many electron system is complicated. So let's say we have a multi-electron system. It's wave function psi. What's psi going to depend on?
Would it be R,
Mm-hmm.
then the psi thing, and
Yep.
the line through it?
Yeah, theta and phi. But now, how many R's do we have to deal with for a many electron system?
Rn.
Yeah, R sub n. So R sub, oops. So like, let's say we have electron 1, electron 2, electron 3, and so on. Where we have many electrons that we have to deal with. Or R sub I, this like thing that we're talking about here, it is the vector from the electron nucleus distance. Okay, so now let's talk about the orbital approximation. So what would you say to make this much easier? Rather than being a function that depends on a ton of different variables, what could you do?
Depends on psi.
I'm sorry, it depends on what?
It depends on psi, which summarizes all those different.
Yeah. Well, yeah, this system does depend on psi. That's true. But I'm saying, what could you do to this psi, this wave function, to make it way easier?
Maybe separate them in some way.
Yeah, you could separate them. What we could say is we could approximate R1, R2, R3, and so on. We could say, hey, what if we separate these? So we get R1, R2, R3, and so on, right? So what the orbital approximation is saying is that each electron occupies. Do I need two P's in occupies?
Or C,
2 C's.
Two C's? Okay, we're good. Occupies its own orbital. And these orbitals are independent.
I want to say it is 2 P's, is it?
No, it looks right. No, that looks weird.
No, no.
I see occupuppies, I don't know. So, okay, so how do you think this approximation is behaving? We have each electron occupies its own orbital and are independent. Is this true?
No.
Right. So this is not true. And why is it not true?
Because they don't.
Yeah. So the electrons aren't independent of one another, right? That's what we were talking about with correlation. They do depend on one another. So this is not true, as electrons depend on each other and interact. But we're going to make that as a first approximation. Okay, we'll get back to this in a moment and we'll see the consequences of that. Before we do that, let's start talking about the helium atom itself, because that's the simplest multi-electron system we can think of. Well, one of the simplest multi-electron systems we can think of. Am I okay to move this up? Okay, let's talk about the helium atom. And this was a question on your last Quizlet. A lot of people did really well at it.
Great job, guys.
What does the Hamiltonian for helium look like? Better. So we want to consider what the Hamiltonian of helium looks like. Symbol for Hamiltonian?
H hat.
H hat, yep. And H hat's always made up of what two components?
Electron nucleus.
So what two components is the Hamiltonian made up of?
Your kinetic
Oh,
energy.
kinetic and potential energy.
Yep, kinetic and potential energy. So we got K and we got V hat, right? Okay. Let's consider the different types of kinetic energy we're going to have. So we're going to have a couple different operators for each of these different types of kinetic energy in the system. And we're going to have some different operators for the potentials that we're going to have. So tell me a kinetic or tell me a potential, or if you're giving me an interaction, I want to know, is it a kinetic energy? Is it a potential energy? And so on. So could you give me any type of interactions in this atom?
One electron to the nucleus interaction.
Okay. So we're going to have it on the first electron with the nucleus. Is that going to be a potential or a kinetic energy?
It's going to be potential.
It's going to be a potential, yep. And let's call this V hat R1. Now, we'll describe the signs in a little bit. We won't deal with that right now. So this is interaction of electron number 1 with nucleus. Give me some other terms.
Kinetic energy of the electrons.
Yep, so kinetic energy of electron number 1, right?
Oh, electron. Okay. Well, I mean, well, could it be like kinetic energy of one electron, but then multiplied by n electrons? Because
Well, the electrons might differ in terms of their positions.
position. Oh, so that would okay. Yeah.
Mhm. So what else do we need then?
So kinetic energy of electron 2 then.
Yep. Electron number 2, any other terms?
Would be the potential of R2.
Yeah. So same thing, interaction of electron number 1, or excuse me, electron number 2 with nucleus. Other things, what else do we got?
We would have the kinetic energy of the nucleus.
Yep. So the motion of the nucleus, anything else?
Then you would have potential of electron-electron interactions.
Yep. So this portion over here, that's the electron-electron interaction. Okay, so now let's put in actual terms rather than just like these nebulous operators. Okay, so kinetic energy, what do we need? What do we always have for our kinetic energy operators? We have that, yep, negative h bar squared over what?
2m.
Yep, 2m. In this case, we're not going to use m. What are we going to use?
I.
Not just m.
Is it
For what?
U?
Is it I?
Nope, not I. We want
Wait, what are we talking
fancy
about?
M.
2. Oh, it's mu.
Yep, that reduced mass, right? Which is a bit different than what we've seen in other cases. Okay, what else do we need for a kinetic energy?
Bring me the derivative.
Yep, we need second derivatives. We're going to represent that as a gradient. And remember, you guys remember what that gradient meant?
D square x plus d squared y,
Yeah.
d squared c, whatever. That whole thing.
Yep. If we have spherical polar coordinates, that's more complicated. We're not going to worry about that though. We'll just write that one for now. Okay, and what do you notice about the sign?
Negative.
Negative, so energy lowering, energy raising.
Energy lowering.
Yep. Okay, next term, what's it going to look like?
The same thing except with electron 2.
Oh. Okay. Next term.
So in the term for mu for electron 1,
Mhm.
since reduced mass is in accordance to 2 different separate masses, what are the 2 masses?
So you tell me, what are the 2 masses in this case?
Yeah,
Or what do we?
an electron and nucleus, or
Yep.
are you talking about?
Yep, electron and nucleus.
Okay.
So because we do have these reduced masses here, do we have to worry about the motion of those nuclei?
No,
Right.
because it's yeah.
Right. So like if we think back to the hydrogen atom that we solved, we introduced this mu so that way we could reduce these 2 terms down to a single term. So we're going to do the same thing here. Okay, we need potential energies. Coulombic potentials, right? So what's that going to
Be
look like?
positive z. What is it? Z over like me something.
E
Z over
squared.
e squared.
Yep, over 4 pi.
Epsilon not r.
Yep. And is it positive or is it negative?
Positive.
Remember, energy lowering.
Negative.
Is this not potential energy that we're talking about?
Yep, it is a potential energy. It's a negative value.
Oh,
Then we're gonna, oh, what do we need to indicate here? What's this R?
1.
Yep. Next term. Or did you have a question, Josh?
so how is a potential energy lowering? Because I mean, I think of like potential energy as in like it's storing energy.
Yep, yeah, you could think of it as like storing energy, right?
So, but if it's lowering the energy, wouldn't that make it seem like it's using the energy?
I think the total energy of the system is lowering. It's just a way of converting it.
Okay.
So I think what you are saying, like,
So
yeah,
what would a positive energy look like then? In this?
like this, it would just be like a plus. Or you mean like what would a positive potential energy be?
Yeah.
You really wouldn't have a positive potential energy for these systems. Oh,
What about a positive kinetic energy then?
actually, I do lie. You will have a positive potential energy. We'll see it in a moment. So
Okay.
like this interaction is the interaction with the electron and the nucleus, right? Is that favorable or unfavorable?
Unfavorable. Opposite charges. Oh wait, no, it's favorable. Yeah.
Yeah, opposite charges, so they're favorable, right?
Yeah.
So this is going to be negative. We're going to have the same thing for electron number 2, right?
Oh, and then it'll be unfavorable for the electron. Okay.
Yep. So what's the sign going to be for this last term?
It'll be positive.
Right. There you go. So that's an example of a positive potential. Okay. Thing to notice, this is R12. And again, why a positive sign here?
Because unfavorable interaction between electrons and electrons.
Right. This is a repulsive interaction. It's unfavorable. Okay. So therefore, all we got to do, we just got to solve this Hamiltonian. Therefore, or excuse me, we just need to use this Hamiltonian to solve the Schrodinger equation. is solve the Schrodinger equation. With this Hamiltonian. But there's a problem.
Right.
It's impossible. But with current mathematics.
We could be the one to change it.
Could be. You would win the Nobel Prize for sure with that. And you would actually, you might also decimate all of like experimental chemistry and physics, because then we just have to punch numbers in. Which would be sad in a way too. Okay, why is it impossible though? What out of this makes it impossible?
The electron interaction at the end.
Yep. Thanks to that damn positive e squared 4 pi epsilon naught r 1 2. Why does this make it impossible to solve?
You can't separate it. The
Yeah.
R1 from R2.
It is impossible to separate into R1 and R2, as R1, comma 2 depends on the position of both. Okay, so does anybody see a way around this? Maybe one we recently talked about.
Probably in matrices.
Well, we're going to get to those, yeah. But any approximations we could make?
You got a constant.
I was thinking that orbital approximation.
Yeah.
Yeah.
John, that is a good fallback, though. P-chemist, whenever we're stuck in a corner, just constant. We're good to go. Yep, we're going to use that orbital approximation. Okay, let's try to justify this. Or at least let's set up how we're going to justify this, because we won't have enough time to solve this. Really rocking out today. Okay, so next time what we're going to do is we're going to justify this for helium. So we're going to go through, we're going to look at that, we're going to start separating out terms, and we're going to show that we can, in fact, do this. Are there any questions about what we talked about so far today?